bases are incredibly important. So this is our big definition that you're really expected to know in Chem 130. You build on this definition in future classes. All right, so our acids are hydrogen ion donors, which in and of itself doesn't really help you out that much, because if you're given a structure and you're asked to predict is it an acid or a base, but no reaction, how can you tell if it donated a hydrogen or not? Okay, you wouldn't have the information available to allow that process. So what would you look for in a structure to know that you're looking at a hydrogen ion donor? What has to show up in it? You have to have hydrogen. All right, well, let's look at a quick formula. What if we gave you this formula? Does that have hydrogen in it? Yeah, it does. Does that make it an acid? No. Okay, so we need a little bit more information for you guys to go through and process this. We can either teach you all of the material behind how you determine what an acid is, okay? So we take you through another semester of chemistry, or we give you a shortcut. Okay? This class is full of shortcuts. That's where we're going to go with this. You have to have a hydrogen, and where does that hydrogen need to show up for you? You need to have a hydrogen in front. Okay? If that hydrogen is in front, you are at a much higher probability of it being an acid. There is one extra thing that kind of falls along with this. When we did acid nomenclature, what was the other clue? You also had to have an aqueous solution. So you have to have a hydrogen in front, and it needs to be aqueous to signify it as an acid. Unfortunately, that aqueous term really only applies to this class and doesn't apply very well outside of this. Okay? So your end all is not that it's aqueous, but that you have that hydrogen in front. If you see the hydrogen in front, you should immediately be thinking acid. Okay? That's the big part of that. When it comes to your base, you're looking at a hydrogen ion acceptor. Again, we run into an issue. If I just give you a structure, how can you decide if that is a base or if that is something else? All right, well, what do you need to look for? Okay. For those of you that were in lab on Tuesday, it might be a little bit easier because that's what our lab was. You need to look for not OH, but OH minus, which happens to be hydroxide. Right? This again becomes a bit tricky because we could go through and pick something that looks like a base. NaOH. Oh, there's an OH. I could also draw out, let's do it this way. Both of those problems, or both of those structures, formulas, have OH. Does that mean they're both bases? No. There's something else going on that makes it a base. Okay, well, we said it had to have what? Hydroxide. OH minus. When do we have OH minus? When we have an ionic bond. That's not how you spell ionic. It's simple enough for me to fix. I'll fix it. When we have an ionic bond, then we can have hydroxide. Well, how do we know it's an ionic bond? You have to have a metal and a nonmetal. Well, hydroxide is our nonmetal, so we have to have the hydroxide bound to a metal. If it is bound to a metal, then it's an ionic bond. If we have an ionic bond, then we have hydroxide, which then means we have a base. So let's take a look at sodium hydroxide. Well, never mind. I just gave it away. We could go through and name the compound, and we have sodium hydroxide. Why can we name it as sodium hydroxide? Because it's an ionic compound. We have an ionic bond. We have a metal in sodium. How do we know sodium is a metal? You look at the periodic table, that bolded line that's running through the right side of our periodic table. If anything's to the left of that, we're looking at a metal. Sodium is well to the left of that, so we've got a metal. Okay? So we've got an ionic bond. We have the presence of hydroxide. So we are looking at a base. How about the other one? Right. Do we have a metal? So we could box out our OH and then say, okay, do we have a metal? Is carbon a metal? No, it's to the right of our jagged line. Is hydrogen? That one's interesting. Why is that one interesting? It's to the left, but hydrogen's one of those elements that isn't classified appropriately on our metallic versus non-metallic situation. Okay, hydrogen is a non-metal, okay, which means what type of bond do we have? We have our covalent classification, or ultimately not ionic. If it's not ionic, can it be hydroxide? No. Which means, is this a base? No. Kind of makes sense? So you have to be careful with some of your approximations and simplifications within this. So that does not supply hydroxide. Is this definition wickedly narrow and horribly inaccurate? Yes. Okay. But for the sake of this class, it works very well to get us through the questions that you would run into. Okay. We also run into an issue which, in a larger lecture, if I'd remembered, I would have actually put in my fancy slide on this. We have a difference between a strong acid versus a weak acid. And of course, if we can differentiate and say there's a strong and a weak, we have to come up with some way to classify those and identify, hey, this one is strong and this one is weak. So we can make people worried about one and not worried so much about the other. Okay, so we have to know what happens. Well, our definition is that our strong acids or bases completely ionize when they hit water. Okay, think back to our acid definition. What did we say our acid definition was? Had to have hydrogen in front and aqueous. What does aqueous mean? It dissociates into the ions when it hits water. Well, there you go. Our strong acids completely ionize. That means when I draw a reaction for a strong acid, when I throw it in water, that's a C, not a U. I completely dissociate into my H plus ions and my Cl minus ions. Right, how do we know it's completely dissociated? Any ideas? Okay, let's try a different reaction. What compound is this? Acetic acid, which when it hits water, because it's an acid, dissociates into ions. So we get our H plus aqueous, and we get our acetate ion, aqueous. How do I know HCl completely ionizes in water according to that equation? When I look at the HCl arrow between the reactants and the products, where does the arrow point? For HCl, it goes only to the products, which means at no point do I have unionized HCl floating around. I have H plus and I have Cl minus. My equation tells me that. When I move to acetic acid, what happens? Now when I look at my arrow, yes, it can completely ionize, but then what happens with the ions? They go back to this compound, which means this compound, acetic acid, does not completely ionize when it hits water. Okay? It's in an equilibrium. Okay? So if we now take this back to our definitions, acetic acid would be defined as which type of acid, strong or weak? A weak acid, because it did not completely ionize. It has that reverse reaction occurring where it's not an ion. And HCl would be a strong acid. Okay, so given the equations, you now have an ability to interpret the arrows and come up with strong versus weak. Okay, except oftentimes what you'll see is something like this. Is HBr a strong acid or a weak acid? With no reaction arrows, we need something else to pull at. How do you know it's strong?
It's on my list.
Okay. There's a magic list. Your strong acids are confined to these 6, sometimes 7, depending on the class. If you are one of those acids, you are defined as a strong acid. What if you're not on that list? Then by definition, you are a weak acid. Same kind of deal applies with our bases. Our strong bases are on this list. Group 1 metals with hydroxide. They have to be hydroxide. And most group 2 metals. Okay, why do we run into an issue with the group 2 metals? There's some kind of weird exceptions. If you look at your solubility rules for the calcium hydroxide, is it soluble or insoluble? I'm not positive on this one. I think it's true. It's actually insoluble, which means it stays as a solid. Can a strong base stay as a solid?
Yeah.
No, it must completely ionize. So we do run into some weird exceptions within these. The exceptions, leave them as exceptions, memorize the rules, work with the rules. Okay? If you're forced to look at an exception, then by all means you have to evaluate it. For instance, if you were given the option calcium hydroxide versus, oh, why not? Let's come up with a couple others. C2H5OH. Oh, and here we go. Lithium fluoride. Which of those 4 compounds is our strong base? What is HC2H3O2? Our second one is an acid. So that can't be the answer. If we look at calcium hydroxide, we just said that that's insoluble, which would suggest it's not a good base. Okay, but it does give us that hydroxide. So for the moment, let's just call it base-ish. Okay. C2H5OH. What's that one? Harder question. It's not a metal, which means not a base. Is it an acid? No, because we don't have hydrogen in front. Okay, so minimally with this, we could say not base. Last one. No hydroxide, no hydrogen, not base. So what's our answer then? The first one.
Why is it on the list?
What's that?
Why is it on the list?
It's on the list because oftentimes you'll see it shown as a strong base. It's a weird one. Okay? So with these answer choices, the only one left is our calcium hydroxide. That's the one we pick. But what happens if we add one more answer choice? What is NaOH? Sodium hydroxide, which absolutely fits our strong base category. So now, given the choice, what's our answer? Our last one. Okay? So we apply the rules as we've memorized them, and then if we run into some weird kind of overlap, we pick the best answer of those weird overlaps. Either way, when we went through and did it the first time, what we did was eliminate answers. Okay? Make sense? You just asked a question. What was your question?
I said, for the first one, the CaOH2, I probably already said this, but why is it base-ish?
Calcium hydroxide is one of those compounds that is insoluble in water.
Okay.
Your strong bases need to completely dissociate into ions. If they don't completely dissociate into ions, they can't be strong. Okay, so that's our definition of our strong whatevers, be they acid or bases. So it has limited solubility. If it has limited solubility, that makes it very difficult to call it a strong base. Make sense? The reason it shows up on the list is because what we've gone through and done is tried to give you rules to memorize. When you memorize a rule, you forget all of the exceptions. So
more importantly than it being on the list is the group 1A.
yes. And where's calcium, though? It's a group 2A metal. So most group 1, almost all, in fact, sorry, let's try that again. All group 1As are strong bases. Group 2A, mostly strong bases. Okay? So the rule that we give you is if you see hydroxide with group 1 or group 2, it works. It's close, not perfect. Okay? So our weak acids and bases are everything else. This brings up the next idea of electrolytes. Okay? The whole point of electrolytes is to allow electric current to flow. Okay? So if you think back to when you're working out or you're running around, okay, or you look at the commercials, because you don't work out or run around. Right? Commercials tell you, Powerade, Gatorade, what are you trying to replenish? Electrolytes. Why do you need electrolytes? Okay. They aren't supplying any energy. They aren't really going for hydration either. Action potential is a fancy way of describing this. What's happening within your brain or any of your muscles? Electric flow. We are electric beings. There is an electric flow that's happening between motor neurons in your brain. All of those things need an electric current. If there aren't any ions, can you pass that electric current? No. So if you're working out and all you're doing is drinking water, well, you start sweating out water and salt, the electrolytes. Those are now no longer in your bloodstream, no longer in your muscles. So when your brain tries to tell your muscle to flex, what happens? The signal dies right at your brain and your muscle doesn't move. Okay? That's kind of a crappy situation if you're an athlete. Okay? If your brain's trying to tell you to move and you don't move, that's a problem. Okay? So we need electrolytes to actually allow for electric flow, both within our bodies and potentially within other systems. So the lab that is performed this week is looking at these various materials. When we add them to water, are they electrolytes? Okay, well, how about a strong acid or a strong base? Would we expect them to be electrolytes? Yes. Because what do when they hit water? They completely ionize, so they completely turn into the ions. We now have ions, which is where our electric flow can happen. Okay, so we can look at strong electrolytes. Sodium hydroxide, sulfuric acid, sodium chloride. All of those are nice strong electrolytes because when they hit water, they completely ionize. They completely turn into those ions. Okay? How do we know that? Well, the case of sulfuric acid and sodium hydroxide, both of those are our strong species. So those are our strong or need to completely ionize. Those have to be electrolytes. But what about sodium chloride? How do we know sodium chloride is an electrolyte? Okay, we could cheat and say, well, we need sodium ions from biology, so that's got to be an electrolyte. Okay, what else? Could look at group 1. What do you mean by group 1? I agree with that. Sodium, what does that mean? What are you pulling from? Sodium is a group 1 metal. Group 1 metals, sorry, I didn't like the way that looked. I had to erase it. Group 1 metals, that doesn't look much better. According to our first rule of solubility, close enough, are always soluble. If they're soluble, what do they turn into? We'd see that aqueous, and we'd say ions. There's our electrolyte. Okay? So we have to pull from those solubility rules that we had to learn way back when we talked about double replacement reactions and predicting those. Okay? What happens with our weak electrolytes? Or we could push even further to non-electrolytes. What's going to happen when we add them to water? They don't ionize, or they don't ionize to a lesser extent. Okay? So if we take a look at some of these examples, how do we know that these are weak? Are any of them strong acids? Okay. None of them are strong acids. How about a strong base? Also no. Okay, so we can eliminate 3 answers based off of that, or 3 problems from being strong electrolytes. What about that first one? How do we predict what that first one's doing? Solubility rules. How many of you memorized the solubility rules to be able to predict calcium carbonate? I'll tell you, I don't have them memorized either. Calcium carbonate is insoluble. Stays a solid. Well, if it's a solid, can it be aqueous? Can it form ions? No. So we don't get an electrolyte with calcium carbonate. It forms a nice solid. Okay? Have you all encountered calcium carbonate before? Seen the ring on bathtubs? Or on any water faucet, that kind of white powdery junk that builds up on it? Guess what that is? Calcium carbonate. Okay? It is very, yeah, I hate this stuff too. It makes a mess. Okay? So it tends to build up and get in the way because it's not soluble in water. It eventually builds up to a high enough extent that it actually can close pipes and all sorts of other fun stuff. Okay? As far as deciding weak versus strong with some of these other ones, we do run into some issues as far as weak versus, non-electrolytes. You don't really have the tools to be able to pick that up and figure that out. Okay? So don't stress too much on figuring out the difference between weak versus non-electrolytes as far as our lecture goes. When we get into lab, we'll talk about it a little bit more in lab to help differentiate those two. Okay? Questions? Okay. Last thing that we'll mention with our acids and bases, we want to go through and think about safety. So we could go through and reference something about the concentration of acid in an individual sample. Okay, so if it's a highly concentrated acid, we say, that's pretty dangerous. Okay, well, what was our units for concentration? Molarity, moles per liter. How many of you have heard of molarity before this class? Okay, before any chemistry class. That's what I thought. Okay, we run into an issue there. Very few people know anything about molarity. So if you're talking to a little kid saying, oh, watch out for that solution, Timmy, that one's going to burn you because it's a 0.15 molar solution in H+. They're going to be, what the hell is wrong with you? Okay? That doesn't make sense. Okay? Take it a step further. 0.15. If I give you $0.15, how rich are you? No. So we look at 0.15 and say, that's nothing. Because if I turn that into something I understand, money, I'm poor. Okay? I don't have anything. Okay, so we don't have a way to wrap our head around those numbers and those values. So we had to come up with a system that allowed us to change all of these crazy numbers and exponential values into something that more people could understand. Okay? So what did we change to? You all have probably heard of this system. Look at the pH. Okay? If you have a really low pH, what does that mean? It's acidic. You have a really high pH, what does that mean? Basic. Nearly everybody responded to that, but nobody knew anything about molarity. Molarity we can use. pH is this weird number that makes no sense. Just means high or low. What was the maximum pH value? Oh, you even knew that. How'd you know those numbers? Okay. What's the lowest pH value? Kind of a trick question. goes negative. What happens when you go to a negative pH? It is really, really, really acidic. Right? Do you guys ever have to work with a negative pH solution? No, I don't think I've ever worked with one either. Right? You're looking at something that is so ridiculously acidic that the pH shifts to a negative value. Right? So it's kind of an insanely concentrated acid solution. So what does pH mean? It still has to come back to an understanding of what's happening. Right? It means log, and in particular, negative log. Right? This is usually where this section of material pops up in second semester general chemistry, and this is where everybody goes, what the hell are you talking about? Okay? You all used logs before? Yeah, some people have, some people haven't. Okay? What it is a mathematical function that can convert really big or small numbers into a meaningful situation between 0 and 14 in our case. So what's happening with our log is we just take the negative log of whatever our concentration of H plus is. When we go through and do that, what happens? We now have a pH. Once we've got the pH, that's what we can then report out and say, oh, that's really acidic or that's really basic. Okay? And now instead of referring to this weird nebulous molarity unit or even weird nebulous concentration numbers that don't seem to really make any sense, we can tell little Timmy, hey, it's a pH of 1. Don't touch that. Or it's a pH of 14. Don't touch that. Or it's a pH of 7. That's okay. Go ahead and touch that. Okay? So it gives us something to relate to and come back to as far as safety. Okay? So your pH is just the negative log of the H concentration. Okay? So could we do other things? Could we take P's of other things? What do you think we would do to calculate the POH? What is that going to equal? What did P mean? Negative log. What is OH? Log of the concentration of hydroxide. So we can determine the POH by taking the negative log of the hydroxide ion concentration. Okay? So we can really take the P of anything we want. All we're trying to do is convert it into a logarithmic scale. That logarithmic scale gives us numbers that we can manipulate and understand and comprehend with our tiny human brains, okay? As opposed to looking at these weird exponential values that could show up within standard concentrations. Okay? Yes? Yes, it is the molarity. So that's your concentration. That is your molarity of H+. Okay? To get into our standard scale of pH. Okay? Could we use a different concentration? Yes, different units, but then we're not looking at our pH scale as we've grown accustomed to it. Okay? Our pH scale is based off of molarity and molarity alone. So if you change the units, all the numbers change, which then means when you take the negative log of it, you're going to get something that doesn't make sense to this scale. Okay?
Just for kicks, I have a calculator out. So do you put, what's the log? Like,
Okay, so everybody's got slightly different calculators, so it may be difficult to find. Give me a sec.
It's up at the top.
There it is, yes.
So just negative log and then,
So what you would do, whoops, on your calculator, so if we did the 0.15, 0.15 log, now take the negative of that number.
take the negative of it.
Yeah, make that number multiply by a negative. Because all we did in that entering was take the log of 0.15. We want the negative log. So negative 1 times the log of whatever your number is. So in that case, the log of H plus was 0.8. Take the negative of that number. What's the negative of that number?
Yeah, it already says negative.
It says negative. So what's the negative of a negative? It's positive. It's 0.8. That's it. That's your pH. Okay? Questions? Anybody else wants me to show them how to use their calculator for this too? I can go through and do that, but that was the last one I'm doing right now. Okay. What we're now going to move into is looking at rate, and we'll talk about equilibrium a little bit too. These are new slides. I haven't posted these, mainly because this goes back to that 1 or 2 questions that you might see on the test at most. So I want you to be thinking more about what's happening within these as opposed to just writing frantically notes or copying these things down. Okay, so there are some things that affect the rate. Well, what is rate? Before we can look at the things that affect rate, what is a rate? What does rate do or measure? Speed. We're looking at a rate for chemistry, so we're looking at the speed of what? Speed of a reaction. Okay, so if we take a look at an individual reaction, just make it simple, A goes to B. Actually, just to make it fun, let's say A plus B goes to C. Here's why it's fun. What type of reaction is this? It's a combination reaction. We took two pieces, we mashed them together and made one. So we got a combination reaction. What things can affect the speed of that reaction? All right, well, let's think about these A and B as 2 particles floating around. For them to produce C, what has to happen every single time? They have to be close to each other. I have to bring A and B within a certain range so that they can now form C, form the bond that makes A and B C. If I don't ever get them close to each other, the reaction can never occur. Okay? So how could I get those 2 particles close to each other? What's that? So we could look at charges. Okay? That could be something about the nature of our reactant. Okay? Do they have some attractive force to them? Okay? There's other things we could do. Concentration. How is concentration going to help us? If we've got this room and I just have these 2 particles, right, and I need to get those 2 particles to interact with each other to make C. Right? It's going to be really, really hard to do that. So what I could do is increase the amount of A and increase the amount of B within this room. Now what happens? Now I'm going to increase the odds of those interactions. So if I increase the amount, my molarity will go up because I have more moles. What else could I do to increase the concentration? Decrease the volume. Instead of working in this big, massive room, let's condense A and B now into this tiny little space. It's now in a tiny volume. When we look at molarity, it's moles per liter. If I make the liters very, very small, what happens to the molarity? Skyrockets. Okay? When we look at what we do as chemists, all we can really do is manipulate moles. Okay? We can do the volume a little bit, but not very well. Guess what biology does fantastically? And by biology, I don't mean biologists, because they aren't very good at it. I mean biology. We look inside our bodies and what our body does. What does it change? When we look at a reaction within the body, you're looking at maybe only 2 atoms or 2 molecules interacting with each other. So the mole amount is ridiculously tiny, which would mean the concentration is really, really small. And if the concentration is really, really small, what does that mean about our rate? Should be very, very slow. So what does biology do to counteract that? When we run an individual reaction inside the body, it doesn't take a volume as large as the room. It condenses it down to a volume that's roughly the size of the 2 particles it's trying to react, which means those 2 particles have nowhere to move except to each other, which means the volume is so small it's effectively nothing. And if we divide a number by a really, 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 really tiny number, what happens? It gets immensely huge. Okay? And so when we look at what's happening within our bodies, our concentration is massive, even though we have very small mole amounts relative to what we would do in a lab. So that's kind of neat. Okay? We could look at the nature of the reactant as well. Okay, for instance, if one of our compounds is a solid and the other one is a gas, where's the only two places that those things can interact with each other? Only at the surface of the solid. So if I want to increase the speed of the reaction, what can I do to the solid? Break it up into smaller pieces. Now there's more surface area, more can react. So we can look at the nature of our reactant. Okay, we can also look at the mechanism, which thankfully you guys don't have to worry about, because that is a really difficult concept. Okay, how does it actually work? Does A have to hit another molecule of A first to make some crazy molecule that then B can impact? Or does A just have to run into B? Okay, so how exactly do we transition from being A plus B to C? Okay, tricky concept. Last one, or second to last one, temperature. Okay, is going to be directly related to our rate. What do we mean? What happens if we increase the temperature?
They react with each other faster.
Why do they react with each other faster?
They're moving faster.
They're moving. Okay, they're moving a lot more. So if I've got Jorge and Jack over here, and I want them to interact with each other. Okay, right now they have relatively low energies. But if I now come along behind them with a fire source and heat them up, they're going to start moving pretty darn fast. Eventually, what's going to happen? They will bump into each other and allow the reaction to occur. But without that energy, without that external prodding on my part, sorry guys, they're just going to stay apart from each other. Okay? Unless I tell them I'm going to do it, and then maybe they'll get up and do it before I burn them. Okay? So if we increase the energy or the temperature, we increase the speed of our reaction because everything starts moving more. Well, the more it moves, we increase the probability of those actually impacting and affecting each other. Okay, so that's what's happening when we increase the temperature. The last thing that we can go through and do is add a catalyst. Catalysts are kind of neat, because what do catalysts do? They directly speed up the rate of the reaction. How do they speed up the rate of the reaction? That's a trickier question. Catalysts change the mechanism. They change how the reaction works on a fundamental level. By changing how the reaction works, they can speed up the reaction. Okay, so kind of a neat process. So let's take a look at, I copied and pasted this slide, I don't know, I'll talk about this. Let's not talk about that one. Okay. Wow, I copied and pasted a lot more slides than I thought I did. Let's take a look at an example here for a reaction. What type of reaction is this? Chemical, fair enough. Try again. Give me more details. It is an exothermic reaction. Keep giving me right answers until you give me the right answer that I want. It's a combustion reaction. We're reacting an organic material with oxygen to generate CO2 and water. Every time we burn something, that's what's happening. We're doing a combustion reaction. Okay? So we've got a general combustion reaction up here. Okay? Why does the log on the left not look like the one on the right? Okay, but it's an exothermic reaction. It releases heat. So if I take oxygen and I take my organic material and I put them near each other, shouldn't they just start burning? Why do they not start burning? There's a barrier that prevents reactions from occurring. That barrier, if it's a big barrier, what happens to our rate? Our rate becomes incredibly slow because it's now very difficult to become products. But what if that barrier to the reaction occurring is very, very low? Reaction happens very, very quickly. All right? So to go through and get the log on the left to look like the log on the right, what do I have to do? I have to add some energy. Once I've cleared that barrier, the reaction can become self-sustaining, and I can continue to burn the log on its own. So what do? We light a match. We provide just enough energy to get our reaction to go. It now self-sustains, and it will continue to combust. Okay? So we had to supply that energy. How do we supply that energy? By increasing the temperature in that local vicinity. That increase in temperature allowed our reaction to start. And that's why we don't see it spontaneously combust. So we supplied that energy. Okay? what part of the log is burning in that fire? Just the outside, which means it's only the surface. So we've got a relatively small area that's actually reacting. What if I want it to burn faster? Break it up into smaller pieces. What happens to the concentration of wood then in exposure to the oxygen? If I break up the pieces into smaller, I have more surface area. The concentration actually goes up. So I'm changing the amount of a species that's actually reacting. Okay, so we can tweak our concentration by changing the phase. So we've got a barrier to that reaction being that phase. Okay? Is there something that we could add to this to facilitate it, to make it go faster? We could add gasoline. Okay? Now the gasoline is going to start to burn and feed up more energy that can help try and facilitate and speed this reaction along. Okay? So we could look at the gasoline kind of as a catalyst. Okay? There's a slight issue with that. You guys remember what I said about the catalysts, or what was on the slides? Catalysts are not consumed in the reaction. When we add gasoline to this, is the gasoline consumed? Yeah, so we'd actually be running two simultaneous reactions to speed up our overall reaction, just to supply more energy to get more things to happen fast. It's not officially a catalyst. All right, so it's not a perfect example, but it gets us through to the idea. So we can change our concentrations and we can change our temperatures to go through and affect the rate of an individual reaction. Okay. Bear with me a little bit. This is going to get a bit numerical here. Okay. How do we monitor all of this? Okay. If we had a bunch of beach balls, we could look at the beach balls bounce around in here, and we can see that. We can visibly understand what's happening with beach balls. When we look at the molecules of wood, and then we're trying to look at them burning, how do we actually monitor the speed of that reaction? Okay, because when we add energy, what happens to the wood? Does the wood start bouncing around and moving more? No, we don't really see that. Okay, so how can we start to quantify what's happening within them? We'd look at time. And what might we look at with that time? The time it takes to burn. What do you mean by burn? It's the time it takes a certain mass of our organic material to turn into water and CO2. So we could look at a change in the concentration of our wood. Because in the process of that burning, what happens to the wood? Does it exist anymore? It becomes smaller. It changes into something else. So what we can do is look at the change of concentration versus the change in time, which is ultimately a rate. So if we look at rates, and this is where it's going to get a bit, or almost a bit jumpy, okay? What we're trying to look at is just how these concentrations change with respect to time. And ultimately, that's all kinetics, that's all rate is. What happens to the concentration of these species with respect to time? Okay, why is that an important thing to do? Well, as a chemist, you go into lab, and what do? You run experiments. What are those experiments doing? Okay, typically, we're trying to make something. Think about the tables that you've got in front of you. Most of that was a polymer. Where did that polymer come from? A chemist sitting in the lab trying to make some material that would be good to write on. So they went into the lab, they mixed some stuff together to try and observe what they could make out of that. Ultimately, it's all chemists are, just trying to make something. Okay? Why does that become important? Well, if we now look at kinetics and rates, if you're a chemist and you go into the lab to make something, and the process of making that something takes 20 years, do you really want to run that reaction? Probably not. That's probably an awful choice. Okay? But if you go into the lab and run a reaction and it happens in 2 seconds, you're probably like, hey, yeah, maybe I'll test that. Okay? That's not a bad reaction to run. So if we understand something about the rates and we can predict those rates, we can go into the lab and say, this reaction is going to go fast. I'm going to test this one. This reaction is going to take 20 years. I need to find a different reaction. So we can change what we're going to do based on that rate information. Okay, so rates are important to us. How do we actually convert this into a quantification system? You'll notice what we have here is we have time, and we have a whole bunch of concentrations, and we can then convert that into a rate. How do we convert it into a rate? We look at the difference in time and the corresponding difference in concentration. When you look at all of this data, does that look really easy to understand? No, it's kind of confusing. What could we do to clean up that data, make it a little bit easier to understand? Okay, I could have come up here and I could have just started talking about wood burning. Okay, talking about wood burning have been very helpful. I know. What did I provide? Pictures. Because pictures make things everything better. Think about when you're a kid. You're opening up a book. The first book they gave you, was like the Iliad, right? Okay. Or maybe something from Dostoevsky. Some big, massive book was just full of text, right? Everybody read that as your first book? Okay, what did you read as your first book? Picture books. Why? Because pictures are pretty. Okay? You come into this class afraid of chemistry. Why? Because what you see is all these stupid numbers. So as chemists, we said, okay, we got to come up with a better idea. Let's convert it away from these numbers. What do we convert it into? A picture. But we still need to retain some of that information. We come up with a graph. Right? And so what someone did was took all of that data and started to generate different graphs and said, at what point does that graph make sense to me? So they start changing what they're plotting. In this case, we're plotting rate versus concentration. Why might they have said, this is an awesome graph? It's a straight line. There is a direct relationship between the concentration and the rate. Why is that important? Well, if I increase the concentration, what happens to the rate? It increases. And it increases in a linear fashion. Lines are a lot easier to work with than logarithms, okay, or exponential values. So once we're in this straight line, we now have that direct relationship. And what we can come up with is say that we have this relationship. We have a direct relationship between the rate of a reaction and its concentration. Okay? So they're proportional to each other. We've seen this before. When did we see that symbol before? All together now. Gases. I didn't expect you to do it all together. It's okay. Okay? We saw that relationship in gases when we related, say, pressure to temperature. What happened to our pressure when we increased the temperature? It went up directly. We have a direct relationship between the rate and concentration. Okay? Okay? That's just a proportionality. If I want to set it up into an equal situation, I have to bring in a constant. Remember when we were talking about constants and symbols that we wanted to pick? And I said K was a horrible, horrible option? This is one of the reasons why. A lowercase k happens to be the constant used when we're talking about rates. It's our rate constant. Okay? So if we're going to look at that expression, we now have a way to relate rate to concentration. Increase the concentration, what happens to the rate? It goes up. Okay? Temperature also falls out of this. But remember how we said we don't like logarithms? To see where the temperature comes in, you got to deal with all sorts of nasty other chemicals and equations, so we won't worry about that this semester. If you go through and take 152, you can see it then. Once we understand everything about kinetics, we can then go through and take a look at a different reaction. Okay, what's happening in this first reaction? Step one. What's special about that first reaction? In particular, why is it different from step two? Reaction goes both ways. Okay? Just like what we said happened with equilibrium. Okay? When we were looking at some of our acid bases, our weak acids and bases. So if we achieve equilibrium, what we're saying is the rate of the forward reaction equals the rate of the reverse. Okay? That's all equilibrium means. So if we have that information, we can go through and look at the rate of the forward reaction, and we can set it equal to the rate of the reverse reaction. Okay? Mathematically, I know you don't like that, but that's what we're going to do. We have the rate of our forward reaction equal to the rate constant for our forward reaction times the concentration of each of our species. Okay? You'll notice what species are happening in the rate of our forward reaction. did I put in NOBR2 into the rate of my forward reaction? Why not? It's kind of a hard question.
Doesn't exist yet.
There it is. Our product does not exist. How can the product affect the rate of the reaction if it's not there? Okay. Are there cases where the product can feed back into it? Yeah, biology. Okay. Biologists have to deal with that when they look at enzyme reactions. Right? There are some cases where a product does feed back and prevent a reaction from occurring. Okay? So if we look at the simplest case, our reaction rate is going to be determined just based on the reactants. If we take a look at the rate of the backward reaction, you'll notice now I have NOBR2. It's kind of weird. Why is it showing up now? What's the reactant for the rate of the reverse? If we look at our reverse arrow, where does it start? With the NOBR2. What's our reactant for the reverse arrow? NOBR2. That's why it can show up. Okay. This is why we saved this discussion for the very last class, because this concept is so stupidly difficult and it takes so much time to actually process and understand and manipulate that at this point when we talked about reactions going left to right, where's your reactant? Your reactant is always on the left. Every time. Every reaction we wrote, where's your reactant? On the left. When you move into 152 and we actually bring in this concept of equilibrium and we really talk about it, where's your reactant? Both sides. Okay? How many of you understand reactions going forward directions perfectly? Left to right. Less than half the class. What happens if we now bring in the concept that reactants are on both sides of the equation? Yeah, exactly. Everybody gives up. Okay? Equilibrium is a difficult concept to understand. What you have to kind of process out of this is Le Chatelier's principle, kind of the balance between those, reactants and products. Okay? And that our equilibrium is ultimately coming from an understanding of the rate. Okay? At equilibrium, the rate of our forward equals the rate of our reverse. From that, we have this fancy little expression at the bottom. See, did I include that next slide that shows this? Maybe. What we can do is then collect like terms. K1 is what? A constant. What is K minus 1? A constant. So let's collect the two constants on one side of the equation. What does the bracket NO mean? Concentration of NO. What's the bracket BR2? Concentration of BR2. What's the bracket NOBR2? Concentration. So let's group our constants on one side and let's group our concentrations on the other. By setting that up, we have a new expression. Come on now. Where we have a constant divided by a constant. What is a constant divided by a constant?
0.
They're not the same constant. One is K1, one is K minus 1. What is a constant divided by a constant? A constant. So instead of writing K1 over K minus 1, let's call it a new symbol. A new constant. This is, remember, this goes all the way back to what we were talking about with K's being a horrible symbol. Guess what symbol we decide for this? Freaking capital K. Okay? That is now our equilibrium constant. And to solve for the equilibrium constant, that's dependent on the concentration of our products over the concentration of our reactants. Okay? So we now have a relationship that can actually tie rates into our equilibrium. You'll notice that when we try and solve for the equilibrium, do we know anything about the rates? Concentration of products over concentration of reactants. Does it say anything about rates? No. Our equilibrium loses information about how fast a reaction goes. Okay? So just products over reactants. Okay? On that, we can leave with the starry sky and say we're done. We've got roughly 10 minutes for questions. Can I go backwards? I can't go backwards. No questions?